So, there we go. That's a bunch of stuff for law number 1. Let's move on to law number 2. Okay? Law number 2. This one, it might not make a lot of sense in the words, but it's actually saying something very, very simple. So check this out. Kepler's second law. A planet moves around its orbit. As a planet moves around its orbit, it sweeps out equal areas in equal times. As a planet moves around its orbit, it sweeps out equal areas in equal times. Okay, so let's figure this one out. This one is a little bit more complicated, but let's try to make it make sense to like a little kid. Okay, check this out. Let me go back to my picture. Okay, let's ignore what Copernicus said. And I'm going to draw an ellipse here. I'm just going to draw one orbit. Okay, and I'm going to draw the sun at one place on the, or at one focus. There we go. And let's say that there's a planet going around this direction on this orbit. So it's following this oval around the sun. And let's say when we first look at it, it's right here. Okay, story. Here we go. Let's say it's your job, like you've been hired to track this planet, okay? You're going to track this planet. So when you very first look at it, it's right there, okay? Now, imagine that there was a giant string attaching the sun to that planet. Let me zoom in a little bit. So say there's a giant string attaching that sun to the planet. It doesn't actually exist, but let's just pretend it's there, okay? And for the sake of this story, let's pretend that that giant string is just covered in glitter. It's just a big glitter string. We like dipped the string in glitter, got it all glittery, and now there's a giant glitter string attaching the planet to the sun, okay? And this will make sense in a second, okay? So check this out. Here we go. Imagine you watch it for a month, okay? And during that month, the planet moves from here to here. Now, that means that during that month, the planet's going to drag its glitter string over, okay? It's going to drag that glitter string over. And we say that that string swept over. It's swept over. So in the law, when they talk about sweeping out equal areas, it's talking about this imaginary line sweeping over, okay? Now, I don't know if you guys have done a lot of stuff with glitter, but bear with me here. If the giant glitter string swept from here to here, what's going to be left behind in this entire area right here? What's going to be left behind if we swing the glitter string over? What are we going to end up with all over space right there? Just tons and tons of glitter everywhere, right? There's just going to be tons of glitter in this giant triangle, right? We've made basically a giant triangle here, and it would just be shiny with glitter. Because glitter is awful. I mean, I love glitter. Glitter's great and all, but I think I still have glitter on me from elementary school. It's just there. Like, I think it just still comes out of my hair sometimes. And I'm like, I haven't used glitter in years, and still sometimes it shows up. I have no idea how this stuff works. Anyway, here's the thing. Let's say while you watch this planet, you watched it for a month, so you made glitter everywhere right here. Okay. But then you got super bored of this. You got super bored of your job, so you stopped watching that planet, and maybe you like binge watched like every show. Like you just binge watch every show for months and months and months and months. You just and then you're like, oh no, I don't want to lose my job. Oh no. And so you look back up at the planet, and unfortunately for you, while you weren't watching it, it's moved all the way over here. Okay? Oh no! So please don't lose your job. You're going to start watching that planet again, okay? So first off, what's happened to our string? When the planet moved from over here to here, what's happened to our string? What's happened? What's happened to that string? Don't overthink this. I'm not getting fancy. It shrunk, right? Yeah, it got smaller. It moved over with the planet, and it's gotten smaller because the planet got closer to the sun. Okay, now, here we go. Don't draw this next part, okay? Don't draw this next part that I'm about to draw, because we'll see in a little bit that there's going to be a problem in what I'm about to draw. Okay, so check this out. Here we go. Let's imagine that planets always go the exact same speed all the time. As they go around their orbit, they've just got like their cruise control on. Let's imagine they never change speed. So if the last time I watched it, in a month it moved from here to here, if it's going the same speed when it's over here, it's going to go to about right there, right? And if I do that, my string would have done this, and I would end up with another glitter triangle. Glitter, that's not a circle, that's a triangle, okay? A glitter triangle right that. But, take a look at this. That planet just broke Kepler's laws. Take it to jail. This planet broke Kepler's laws. Lock it up, right? How did it break the law? Let me go back to the law. As a planet moves around its orbit, it sweeps out equal areas in equal amounts of time. How is this a broken law? What's wrong with what I just drew here? What's wrong with this? What's wrong? Why does this little triangle here break the law? Remember, again, as a planet goes around its orbit, it needs to sweep out equal areas in equal times. Yeah. Is the area of this triangle equal to the area of this triangle? No. Okay? It's not the same size triangle. It's never going to be the exact same shape triangle because the triangle has to be shorter over here. So here's the question. What would this planet have, if the planet started right here that month, what would this planet have to do in order to make this short triangle equal the area of the big one, of the tall one? What will this planet need to do? Yeah, it's gonna have to go farther that month. Because it's stuck with a shorter triangle, it's got to cover more area. It's got to go farther along the orbit to get that triangle fatter to make up for its shortness. So yeah, that means that the planet, and you can draw this, in that month would instead have to move all the way to here and make a much fatter triangle to equal the area. This short fat triangle can have the same area as this long thin one, right? So that means, here we go, if, let's put it all together, if that planet moved farther in that month, what does that mean about its speed right there? If it had to move farther this month than it did in that month, what does that mean for its speed right here? It's faster. Exactly. Exactly. So what this means is, what law number 2 is really trying to say is that planets don't go the same, they don't just go one speed as they go around their orbit. They're constantly changing speed. And let's be a little bit more specific here. When is a planet fastest? When is a planet going to be the fastest? When's the planet going to be the fastest? When it's closest to the sun. So as a planet moves around its orbit, from here to here, it's getting faster as it comes over here. And then as it swings around, when it goes along this direction, it's going to slow down. So the absolute slowest place on an orbit is the aphelion that we talked about a second ago, the farthest place from the sun. And the absolute closest place to the sun, the perihelion, is the absolute fastest. So basically, law number 2, instead of trying to remember it this way, what law number 2 is really trying to say is that as a planet goes around its orbit, it goes faster as it gets closer to the sun and slower as it gets farther away. Planets are faster on their orbit when they're closer to the sun. That's law number 2. So if I ever asked you to explain law number 2 to me, I don't really want to hear this. Whenever I ask you to explain something, I want you to explain it in the way that like a middle schooler could understand it. What is Kepler's second law? Planets go faster when they're closer to the sun. Boom. Okay.